Okay. So yeah, Devansh, please do attend the class. It's it's okay. Yeah, please do attend the class. That's fine. Okay, so let's begin the session for today. Thank you everyone for joining in. This is one of the 4 sessions or 3 or 4 sessions that we have planned for this year's NMTC. And we will see that, yeah, that's great. So we will see that the concepts of NMTC is kind of similar, stage 2. It's kind of similar to RMO, the Regional Math Olympiad. It's a bit easier than that. So I guess that's great. But we will be learning some of the stuff that is relevant to both NMTC and RMO. So I think it's useful for you anyway. There are, as usual, we will have 4 concepts, 4 key areas: geometry, number theory, algebra, and combinatorics. And of course, you should go through the past paper. So I'll give a link of that to you at the end of the class. Of course, the past papers are also available very easily. They are available online. So you can also look into them. Now, today, okay, so Cherish has all the past papers. That's great, Cherish. So so you can also share it with your friends. Now, once we'll try to go through each of these separate tools and understand how to employ them in some of the problems. That's how what our plan for this sessions are. So we'll start with number theory, and then we can slowly go into geometry and other parts of mathematics. Okay, so in number theory, we generally start with the notions related to divisibility. So so if you start with divisibility, you basically want to manipulate GCDs, or greatest common divisors. You want to talk about modular arithmetic. You want to understand the Euclidean algorithm, and there are some residual concepts related to divisibility tests and stuff like that. So we will probably not go into that. Okay, so let's talk about a few of these things in the context of this contest. So modular arithmetic is one of the most important tools that you can encounter, and I'll give you an example of what I mean by that. So if you have not seen modular arithmetic before, here is a very quick introduction to it. Suppose you have 2 numbers, A and B. Then you say that A is congruent to B modulo M if M divides A minus B. This is the definition. A is congruent to B modulo M if M divides A minus B. So this is a very simple sort of definition that we use, but turns out that this is an equivalence relation. So who among you understand what an equivalence relation is? Okay, so is Cherish saying something? I think Cherish is saying something. Oh, I should record. You're right. So yeah, he says that he understands it. That's great. So others probably do not. So let me quickly say what is an equivalence. Yeah, sorry. Okay.
So equivalence relation is something that is reflexive, transitive, and forgot the third one, sir.
Reflexive, transitive.
Symmetric. Yes, sir.
Transitive and symmetric. Correct.
Yes, I know them.
Okay, so what does that mean? That means that if A is related to B, then B is related to A. That's what reflexive is. Okay. Yeah, no, sorry. I'm sorry. This is what symmetric is. This is what symmetric is. Okay. Transitive means if A is related to B and B is related to C, then A is related to C. That's what transitive is. And everything is related to itself. So that's what reflexive is. So can you tell me whether this relationship is uh, reflexive? Okay, so if A is congruent to B modulo M, this congruency relation, is it reflexive? Well, of course it
Yes,
is, because A is congruent to A modulo M, because M divides A minus A.
Excuse me, sir.
Go ahead.
Sir, like I'm from level 2B and I got a mail like, would you like to join the NMTC boot camp? So I joined it. So like,
How little you are? How little you are? That's the question. Which class are you in, little Krishna?
level 2B.
No, you are in which class in school?
Level 2B. I mean, like, for now, fifth. I say fifth.
Which grade are you in?
Fifth, sir.
Fifth grade. It
Yes,
might
sir.
be a little less than what we have here, but if you want to hang around, you can. Do we have any fifth graders here? I'm not sure. Are any?
Sir, I'm in
sixth Sir, I'm in sixth grade.
I'm actually fifth.
Now I'm in sixth.
ITH.
Okay, so that's all right. Fifth, Krishna, if you want, you may leave. If you want, you may stay. That's fine.
Sir, I want to study more. So can I stay?
Yeah, sure, you can stay, but don't get
Yes,
scared. That's my
Yes,
point.
sir.
Okay, you're just having fun. All right.
Sir, actually, I'm not Little Krishna and I'm Raja Alangaran. I think you know me.
You are what?
Raja Alangaran.
Oh,
You know
Raja
me, sir.
Langaran. Okay. I see. Yeah, I know you.
Yes, sir.
Okay, yeah. So this is true. Transitive is true. Why? Because if A is congruent to B and B is congruent to C, then A is congruent to C. Why is that? Can anyone put an argument quickly in the chat? Put an argument quickly in the chat. Why should that work? Excellent. We are getting some beautiful ideas. So basically, if M divides A minus B, therefore we can write A minus B is equals to M times some quotient. If M divides B minus C, which is the second one, then B minus C is equals to M M times some Q2. So we can just add these two equations. We get A minus B plus B minus C is equals to M times Q1 plus Q2. Negative B, positive B cancels out. So A minus C is M times Q1 plus Q2. So basically A minus C is divisible by M, which necessarily means A is congruent to B modulo M, right? So we have this simple but useful transitivity rule. Finally, do we have the symmetric rule? Okay, so if A is congruent to B, is B congruent to A? Of course, if M divides A minus B, then certainly M will divide B minus A, right? Okay,
Yes.
so what happens? So this much I think all of you understand. The really interesting part of this entire story of equivalence relation is that it induces a partition. It induces a partition of the set. So I will tell you what that means. Basically, you start with a set of numbers. Let's say 1, 2, 3, 4. Let's say all the positive integers. Let's take all the positive integers. And let's decide on a reference number m. Reference number m. So what could be our reference number? Can you give me an example? Maybe 6. Who knows? We can take 6.
Yes, sir, I was going to say that only.
Okay, 6 is an example. So what we will be defining is something called equivalence class. So what does equivalence class mean? Basically, you take a number, you take all the numbers which is congruent modulo 6 to that number. So what can we put here? Okay, can anyone tell me a couple of numbers? Okay.
So 7,
Minus
13.
Minus 5 also.
So 1 is
Yeah.
there, 7 is there,
7.
because
13,
1 is congruent to
13.
1 modulo 6. 1
Yes,
is
sir.
congruent to
Actually, the form is 6k plus 1. Yeah, sir. It's already written in the public chat too.
Okay, very nice. So what we have is let's write square bracket 1. Let's write square bracket 1 and let's put in all the numbers which are congruent to 1 modulo 6. This set contains all numbers which are congruent to 1 modulo 6. So for example, we have 1, 7, 13, 19, 25, etc. Okay. So what is box of 2? Can anyone tell me? This is one equivalence class.
Sir, 2,
Sir, 2, 8,
8, 14, 20,
2,
26.
15, 20, 26. And sir, it should be 6.
It should be 6k. 6k plus 2.
Yeah.
It is 6 plus 2. Yeah, of course. So we have all numbers which are congruent to 2 modulo 6. So these sets are known as equivalence classes. These sets are known as equivalence classes. Okay, so what do we want to show is that the equivalence classes are mutually exclusive and exhaustive. So what does that even mean? Can anyone tell me what is the meaning of mutually exclusive? So if I say box of 1, the equivalence class of 1 and equivalence class of 2 are mutually exclusive, what do you think is the meaning of that sentence? Devansh is saying that their intersection is phi. So basically, they do not have anything in common. They do not have anything in common. What about exhaustive? What does the word exhaustive mean? Can anyone tell me what is the meaning of the word exhaustive in this particular context? What is the meaning of the word exhaustive? Exactly. So basically, if you take the union of all these equivalence classes, if you take the union of all the equivalence classes, you will get the entire set that you started off with. Take an example with this problem. The equivalence class of 1, so there will be an equivalence class of 0 as well. Stuff that is in the equivalence class of 0 will be 0. Well, we are just working with positive numbers. So 6, 12. Oops, sorry. My father seems to be calling me. Bring back later, maybe. Okay. So 6, 12, 18, 24, and so on. Similarly, we have 1, we have 2, we have 3. Okay. Let's see. Okay, we have 1, we have 2, we have 3. So can anyone tell me how many equivalence classes are there altogether? There are 6 equivalence classes, right? So you have 1, okay. You have 1, 2, 3, 4, 5, 6. There are 6 equivalence classes. Or if you don't take 6, you can make 0, I guess. So that's fine. So you have 6 equivalence classes. No 2 equivalence class will contain the same element. No 2 equivalence class will contain the same element. And and if you, okay, so let's say, so if you take the union of all the equivalence classes, 0, 1, 2, 3, 4, 5, and 0, you take the union of all of them, you will get the entire set of numbers from 1 to infinity. You'll get the entire set of numbers from 1 to infinity. Now my question is this: how can you prove this for an arbitrary equivalence relation? So here is a question that I want to ask all of you. So maybe I can just a second, just add some more boards here. Okay. Okay, so we have some more boards, which will be helpful, I hope. So how can you show that if R is an equivalence relation on a set S, if R is an equivalence relation on a set S. So this is not the usual equivalence relation that we just learned. It's not the congruence relation. It is any equivalence relation. If R is an equivalence relation on a set S, then show that the equivalence classes are mutually exclusive and is exhaustive, which basically means that they induce a partition. So it's a divide the original set into several disjoint pieces. So induces a partition on the original set. So how can you show this for any equivalence relation? We just took an example of one equivalence relation. How can we show this for any equivalence relation? That's the question. Okay, before we go to that, can anyone give me example of any other equivalence relation that you know of? Congruence is one equivalence relation. Is there any other equivalence relation that you were aware of? Can you tell me that?
Sir, the congruency of triangles.
Congruency of triangles is an equivalence relation, indeed. So if you have a set of all triangles, all possible triangles, take the set of all triangles. Please stay muted if you're not speaking. Set of all triangles, then congruency of triangles is an equivalence relation. Can anyone tell me, is similarity of triangles an equivalence relation?
Sir, I don't think so. I think it is. Because similarity is a ratio.
Similarity is a ratio. I have a response from Ashir. A divides B, where A and B are natural numbers. We will examine that as well. But let's see if similarity works. So similarity. Firstly, is it reflexive? That is a triangle similar to itself?
Yes.
Of course,
Yes.
it is reflexive. Is it transitive? That is, if
Yes.
a triangle is similar to another triangle, and then it is similar, and this another triangle is similar to another triangle, then will this smaller triangle be similar to the larger one, maybe in the picture?
Yes, this is also true.
That's transitive. Okay, transitive works. Okay, that's great. Looking good so far. What about the third case? Is it symmetric? That is, if this white triangle is similar to this blue triangle,
Yes, sir.
will the
This will
blue
always
triangle be similar to the white triangle? Of course, that works.
Yes, sir.
So that is the definition. That is the definition, by default definition, of equivalence relation, if these three things happen. So yeah, similarity is an equivalence relation. Let me ask you a different question. This is something commented by Ashir Malhotra. He is also, I think, a student. He commented that A is related to B if A divides B. Is this an equivalence relation?
Only if A is equal to B.
Well, that's not true for all numbers.
So, sir, I know, then it won't be. I don't think so.
Okay, so which one will fail?
The symmetric.
The
A divides B, then B divides A will fail.
Okay, what happened just now? This is very weird. Just a second. My entire kind of thing.
So we can.
You can still see it, right?
Yes, sir.
This is quite weird. My tab sort of stopped functioning, and then it's working again, I guess. Okay. All right. So this is it. Okay. So the reflexive part is okay because A divides A. Every number divides itself. That's fine. So reflexive is okay. Transitive, A divides B, B divides C, implies A divides C. Transitive is fine.
It is true.
But symmetric will not be true.
Symmetric will won't.
Symmetric
It
one
will work
fails.
only if A is equal to B.
Excellent. So Ashir has a very good example actually. It's a kind of a counter example. He gave us an example of a relation where two numbers can be a relation can be reflexive and transitive but may fail to be symmetric. Very nice, very nice. So we are understanding what's going on. Let's use the divisibility sort of stuff to solve some problems. I mean, this is the modular arithmetic in general. let's try to use it to solve a problem. Okay, so here is a problem that we have a positive integer n. N is a positive integer. Those of you who are a little bit younger, don't. I'm kind of always worried that you will get a little overwhelmed or anything. So don't be overwhelmed. If you are unable to follow, that's fine, I guess. We're just having some fun with mathematics. Okay. All right. So n be a positive integer. Show that we have to show that if a and b are integers greater than 1, so we have given two integers greater than 1, such that 2 to the power n minus 1 is equal to ab. So I'll give you an example. 2 to the power 5 minus 1 is equal to 31, right? So so a could be 31, b could be, I don't know, 1. Okay, 2 to the power 6 minus 1, this is how much? This is 63. So a could be 7, b could be 9, something like this.
Sir,
Excuse me, sir.
can't be one,
Sir,
right?
Sir, because they are greater
It's
than
given
1.
as greater than 1.
Yes.
Sorry, what was the question?
Sir,
Sir,
B is
actually,
greater than
written
1.
that A and B are greater than 1. So how can B or A be 1?
Oh, then this example fails. The first example fails, but the second example holds, I guess, right? So
So 2 to the power n minus 1 cannot be a prime number.
it could be. I just gave an example, like
Because
2 to the
A and B
power.
both are greater than 1.
Yeah, 2 to the power. In this case, of course, we are not allowing prime numbers. Yes, that's correct. Yes. Okay, so we have this thing going on. That's great. Now the question is, okay, so we understand that it's a product of two numbers, a and b. Okay. Okay, so yeah, I think Aryan has seen this problem. So we are basically willing to write ab minus a minus b minus 1 as some constant times 2 to the power a power of 2, to the power an even power, in fact. Okay, so where k is an odd integer and m is a positive integer. So that's great. Yeah, I think this has been discussed. So okay, this is an assignment problem. Oh, so did you solve it? It is an assignment problem. Okay. Okay, that's great. It's a popular problem, it seems. Okay. Okay, that's great. So those of you who have not done this problem, why don't you try a little bit this particular problem. And then I can ask the students, in fact, for a little help on this with hints and everything. So that's great. Okay, can't see the problem.
Sir,
Okay,
what do I have to do in this problem?
So the problem says that there are two, you are able to write 2 to the power n minus 1 as a product of two numbers, a and b. Okay, where a and b are greater than 1, integers greater than 1. You have to show that ab minus a minus b minus 1, this quantity is actually an odd integer k times an even power of 2. An odd integer k times an even power of 2. That's the question.
Okay.
That's what you have to show. And I'll tell you one thing, that this particular object, this comes up over and over again in mathematics, in Olympiad style problems. And there is a very simple factorization of this. So okay, so maybe you can just look into this one. A minus 1, B minus 1, A plus 1, B minus 1, A minus 1, B plus 1, and A plus 1, B plus 1. Just keep these 4 tools in mind. They're so simple, but we tend to forget them when we are actually solving problems. These kind of expressions always sort of go up to this factorization. So the first one becomes AB minus A minus B plus 1. The second one becomes AB minus A plus B minus 1. Third one becomes AB minus plus A minus B minus 1. And finally we have AB plus A plus B plus 1. I have seen
Sir, I think think that like I have found the solution.
Okay, Mansha has
Yes,
says that he knows how to do this problem, and there are other people who are saying we have done this problem already. So I will ask them about this. So okay, Ishan. Okay, so ATG is saying, and I think ATG is Ashrit. Maybe that's the name. Ashrit, is that you?
Yes, sir.
Okay, awesome.
It's me.
Yeah, of course. So this Ashrit is saying that okay, we can factorize this as A plus 1 times B minus 1. So this is the first step. Look at the factorization. Okay, so anyone else?
Sir, I actually had an idea after this.
Okay, go ahead, Man. Or Ishan, okay, go ahead.
Uh, yes, so I was like, so if 2 to the power n minus 1 is always an odd integer, right?
Yes.
So its factors also have to be odd.
Uh-huh.
So
All of
a
this.
plus 1 and b minus 1 both are even integers.
Oh, okay. So A plus 1 and B minus 1 are both even. You see, that's a very good reasoning actually. What Ishan is saying, that if you can write 2 to the power n minus 1 as A times B, then this is odd. Obviously, if you are subtracting 1 from a power of 2, so of course that's odd. So A is odd, B is odd, and now we use Ashrit's factorization, which is A plus 1 times B minus 1. So A plus 1 is even and B minus 1 is even. So this is even times something. So even times, of course, odd. Every even number can be written as odd. There is no big deal in it. can be written as even times odd. Why is that? Well, it's kind of trivial that if you take away all the powers of 2,
Yes, sir, because even into odd is even.
yeah, so basically this is, if you take 6, you can write it as 2 times 3. You just extract all the highest powers of 2. It's no big deal, right? And if it's like 32, a power of 2, you can always write it as 32 times 1. So every even number can be written as like this. So our answer, we are kind of one step toward the answer. We basically extracted all the powers of 2 and left out with an odd number, which is fine. So how do we get an even power of 2? Yes, Rajalanganan, yes. How do we get an even power of 2? So how can we be assured that a plus 1 times b minus 1 has an even number of 2's? That's the question. A plus 1 times b minus 1, where this one is even and this one is even, we know. How do we know that there are an even number of 2's? How do we know that?
I want
Okay.
to say something.
Okay, yeah, go ahead, please.
So I don't know, like I'm not able to understand how we'll find the answer to this question, but I understood, like I got some hint that if there are even power of 2, that means the number is always a square number.
It is a square number, yeah. If there is a 2 to the power 2m, then that's basically 2 to the power m whole square. Yeah, that's correct. Okay, anyone else can help us with this?
Sir, I don't think. So I don't think this would be true, because if we take a plus a as 3 and b as 3, you get 4 into 2, you get 2 cube.
Okay, but remember how AB was formed in the first place. We cannot take any AB. AB is 2 to the power n minus 1. So this AB is coming from there.
Sir, in the limiting case, AB must be divisible by 4.
What do you mean by limiting case?
When there is least AB, 4 must be divisible by 8.
Yeah, these must be divisible by 4. That's true. But we want to show that the highest power of 2 that it can divide is not 4. It's it could be some even power of 2. Okay, so we have some raised hands here. Ishan Paul has a raised hand. Go ahead, Ishan. What do you think?
No, sir, actually raise that hand for the property which I just said right now, that even times even.
Okay, fine. Okay, so I'm very close to asking the people who are who have solved it for their method of solution. So I'll just allow a couple of minutes more for you to think what's going on. Okay, so let's go ahead and ask for the next step from the people who have solved it. So Aryan, what do you think? Do you have an idea of how to do this? You say that you already solved
So
it.
as far as I remember, so the person, I had not got the solution at first as well, but somebody had given a solution and said that the highest power of 2 that divides a plus 1 and b minus 1 are equal.
Okay, so the same
I
number
remember
of
the proof for
2's,
that.
the same number of 2's will go into a minus 1 and a plus 1 and b minus 1. Okay,
Yes, sir.
that's what Arav is saying. Okay, let's see. Shaurodip can, okay. So we have to show that the number of 2's, let's say 2 to the power k1 divides a plus 1, at 2 to the power k2 divides b minus 1. We want to show, because we already showed that both of them are even numbers, right? Both of them, a plus 1 and b minus 1, they are both even numbers. We already know this. How do we show that if the highest power of 2 that divides a plus 1 is 2 to the power k1, and the highest power of 2 that divides b minus 1 is 2 to the power k2, how do we show that both of these k1 and k2 are equal? That's the goal. So I ask you to think a little bit again, all of you. I mean, it's no point to give just the solution. We have to deliberate what's going on here. Okay, Ashir is saying that that's great. So those of you did not solve it yourself, you have the opportunity now that you can now like sort of try it on your own. If you just looked into the solution, it makes sense to try it. So we have, so suppose okay, Devansh is saying I did it with a very different method. Okay, what did you do, Devansh? Tell us what you tried. So we have the other proof where you can try k1 is less than k2 and show some contradiction. Oh, okay. Devansh's method is really long. All right, let's not then talk about it. So what do we have so far? We have ab minus a minus b minus 1 is equal to, okay, so a plus 1 times b minus 1. Okay, so we have the following information so far, that a to the power n minus 1 equals to ab, and this is equal to a plus 1 into b minus 1, and we know that a plus 1 is even, b minus 1 is also even. So this is 2 to the power k1 times odd 1, and this is 2 to the power k2 times odd 2. We have just extracted the highest powers of 2 from each of these pieces. We just want to show that k1 is equal to k2. That's what we like to, that's what we want to show. Our goal is to show k1 is equal to k2. So how do we show it? Okay, the first question is, can we say that k1 is less than n and k2 is less than n? Is that right? Can we say that?
Yes, sir.
Okay, how can we say that? How can we say that k1 is less than n and k2 is less than n?
Because a plus 1 is less than ab plus 1 and b minus 1 is less than ab plus 1.
Yeah, it's kind of easy as well, right? A plus 1, this one is certainly less than ab plus 1. 2 to the power n is just ab plus 1, right? 2 to the power n is just ab plus 1. So a plus 1 is less than that, and b minus 1 is certainly less than that. So we have, and this is exactly equals to the power k1 times, this is equal to the power n, to the power k1 times some odd, to the power k2 times some odd. So clearly to the power k1 is less than to the power n, otherwise this wouldn't have happened. Okay, so okay, this is plus 1, yeah. Right, something, okay, yeah. All right, so how does that help us? So we know this, we know this much. So we also know, what else do we know? We know that so we have to fix a divisor. So what is our divisor here? Our divisor is, so what do we know? We know that a plus 1 is equal to 2 to the power k1 times odd, and we know that ab plus 1 is equal to the power n, which is greater than 2 to the power k1, right? So we have two things. We have 2 to the power k1 divides 2 to the power n, and 2 to the power k1 divides a plus 1. We have two pieces of information here. Now we can use some amount of modular arithmetic here. Modulo 2 to the power k1. So how do we do it? So we have, okay, so this to the power n is just ab plus 1. So I did this problem some time ago, so I don't clearly remember, but maybe this was how we can go about it. So ab plus 1 is congruent to 0 mod 2 to the power k1. Right. So this 2 to the power n is ab plus 1, right? So 2 to the power k1 divides ab 2 to the power n, means 2 to the power k1 is congruent to 0 mod 2 to the power k1. Okay. And then we also have a plus 1 is congruent to 0 mod 2 to the power k1. Okay, so that's great. So what do we know? What can we say then? We say that ab plus 1 is congruent to 0 mod 2 to the power k1, and a plus 1 is congruent to 0 mod 2 to the power k2. So you can say something now. You can do something with this pairs of congruences. Well, there is something funny here. You see, AB is congruent to minus 1 mod 2 to the power k1, and A is also congruent to minus 1 mod 2 to the power k2. You could do something similar with 2 to the power k1, k2. Sorry, I'm just, everything should be k1 here. So the second equation was like this, that b minus 1 is 2 to the power k2 times odd. This basically means b minus 1 is congruent to 0 mod 2 to the power k2. And we also have 2 to the power k2 less than 2 to the power n, which is equal to ab plus 1. So ab plus 1 is congruent to 0 mod 2 to the power k2. So B is congruent to 1 mod 2 to the power k2, and AB is congruent to minus 1 mod 2 to the power k2.
So shouldn't AB plus 1 be equals to 2 power n?
Sorry?
So shouldn't AB plus 1 equals to 2 power n?
AB plus 1 is 2 to the power n. Yeah. Why? Because 2 to the power n minus 1 is AB, right? I just took the plus 1 to the right hand side.
So then why did you define k2 again?
2 to the power k2 is equal to times odd is equal to b minus 1, right? That's how we define. So we have two even numbers multiplied to each other. We have two even numbers multiplied to each other, and yeah, we have two even numbers multiplied to each other, and we named each even number. We sort of wrote each even number as a power of 2 times odd, right? So a plus 1 we wrote as 2 to the power k1 times odd, and b minus 1 we wrote as 2 to the power k2 times some odd. That's why the k2 is coming into place. Okay, so some of the folks are already giving us solutions in the chat, the final step of the solution, in fact. So Aryan Prakash is saying multiply the second one by b and subtract it from the first one. What do you mean by second one? Oh, you are saying
I was talking about the first two lines.
these two lines?
So the right side, left side, sir. Sorry. The AB plus 1 and the one with mod 2k plus 2 to the power k plus 1 on the left.
Oh, this one?
Yes, sir.
Okay, so you want me to multiply b to that bottom one, is that right?
Yes, sir.
Okay, let's do that. Let's see what happens if we do that. So a good thing about congruency is that you can multiply stuff on both sides, just as you can do with equations. Like if x is congruent to y mod m, then you can multiply a constant number to both sides and it will still work. And those of you have not seen this before, I'll quickly tell you why it works. If x is congruent to y mod m, this basically means m divides x minus y, or x minus y is equals to m times some quotient. Okay, so now what you can do, you can multiply a constant to both sides of this equation. So kx minus ky becomes equals to m times q times k. So this means m divides kx minus ky, which basically means kx is congruent to ky modulo m. This is the meaning, this is the definition. So in other words, we can simply multiply k to both sides. We can simply multiply k to both sides, right? Okay, so now let's do what Aryan is saying. We have to multiply by, you're suggesting multiply by b on both sides, right, Aryan? So
Yes, sir. And then subtract that first one.
okay,
I mean,
so
subtract the first one from this.
okay, so ab plus 1 is congruent to 0 mod 2 to the power k1, and ab plus b is congruent to 0 mod 2 to the power k1. Now you can subtract these two. So if you do that, you have from the second one, let's subtract the first one. So you have b minus 1 is congruent to 0 mod 2 to the power k1. So b minus 1 is divisible by 2 to the power k1. B minus 1 will be divisible by 2 to the power k1, which basically means 2 to the power k1 divides b minus 1. But I think we started with the assumption.
But sir,
Sorry?
but sir, like b minus 1 is also divisible by 2 to the power of k2.
B minus 1 is also, actually we started with the assumption that k1 is greater than k2, right? If both of them are not equal, then obviously one of them will be larger. Then we can start with the assumption that k1 is greater than k2. But then we know that the highest power of 2 that divides b minus 1 is smaller than k1. That was our initial assumption. But that's a contradiction, because we just showed that 2 to the power k1 divides b minus 1. Okay, so what if the other way, what if it's other way around? If k2 is less than k1, k2 is greater than k1, how can we get an contradiction from this? Well, the
So we use the other.
we have to use the other part, the one that I wrote down here, the next second line, second set, actually this one. So maybe that would be your homework, so you can try this. We and also I will send out the papers of NMTC. You all have it, I think, but I think there are about 20 days left, so you can work really hard and try to solve all the problems from NMTC stage 2. And I will announce also the next meeting that we will have. And if you have some doubts in the problems of NMTC, so firstly, do not read the solutions that are given online. It's kind of boring to read solutions. Don't do that. Ask a friend if you can. And if you are stuck with a problem, then please email me at helpdesk@cheenta.com, and I'll try to work on it and give you some hints. Do not read solutions. Instead, ask for hints. Ask for hints from your friends if you can. Okay. But do not read solutions. I will message you about the next session on NMTC stage 2. Until then, take care, everyone. Bye. Oof.